Welcome to this lesson on Taylor polynomials. Let me start by telling you what a Taylor polynomial is. You start with two things. One is a function that you're interested in doing something with, and the other is a particular point, x equals a. So here we're thinking in the context of functions of one variable. And what a Taylor polynomial is an approximation of the function f near x equals a. And it's a polynomial approximation. We want polynomial approximations because polynomials are really easy functions to deal with, right? You know how to integrate them. You know how to differentiate them. There's no sort of analytical issues. So this is why this is a useful thing to do. There are many applications of Taylor polynomials, and in later lessons you might see some of them. But let's get into the mechanics. How do you actually do this, all right? Well, first, we're going to start by letting our function f of x equal a polynomial of this form. So it's a constant plus another constant times a first degree term plus another constant times a second degree term, and so on. And all those terms are centered around the point x equals a. That's the point we've chosen to approximate around. And you notice that if you plug in a, all these terms cancel out, and you find that f of a equals c naught. So if this is the form of your Taylor polynomial, we know that c naught has to equal f of a. What are these other coefficients, c1, c2, and c3? We're going to figure out by taking derivatives. So I differentiate each side. I get f prime of x equals c1 plus 2c2 x minus a plus 3c3 x minus a squared, and so on. I plug in a, and I get f prime of a equals, and all these terms go away, and I'm left with c1. So f prime of a equals c1. Let's take a derivative again. If you do it, you find that f double prime of a equals 2c2, or c2 equals 1/2 f double prime of a. Okay, and you can do this another time. You're going to find that f triple prime equals 6c3, so that c3 equals 1/6 f triple prime of a. And if you take that and put it all back in, you find this formula for f of x, right? It's the function evaluated at your point a plus the first derivative evaluated at that point times x minus a plus 1/2 the second derivative times x minus a squared, and so on. Okay, common pitfall for students is that you will forget to evaluate these derivative terms at the point a. Don't forget that. That's really important. Okay, so you've taken some function x that's not a polynomial, and you've expressed it in some form that is a polynomial. And a property that these have is that the value of the function and all of the derivatives agree. So the value of the function f on the left equals the value on the right. The first derivative of f equals the first derivative of this long polynomial on the right, and so on. So that's the property of a Taylor function, or Taylor polynomial approximation, is it matches the original function really well at the point a around which you choose to expand. In general, this is the formula. It's f of x equals some sum starting at n equals 0, going up to some degree that you might choose, of the nth derivative evaluated at a over n factorial times x minus a to the n. The sigma notation, to remind you, means you just keep adding on the successive terms. So to make this really concrete, let's do an example. Let's approximate natural log of x at a equals 1, and let's go out to 4th degree. And when I do this, I like to pre-compute the derivatives to use in this Taylor's formula. So my function is natural log, the first derivative is 1 over x, the second derivative is minus 1 over x squared, and so on. And then I can evaluate each of those derivatives at my point a. The value of the function is 0, the value of the first derivative is 1, then minus 1, then 2, then minus 6. Then I just have to plug into Taylor's formula. So it's the function evaluated at the point a, that's 0, plus the first derivative of the function, which is 1, divided by 1 factorial, times x minus 1 to the first power. Then I have the second derivative, which is negative 1. I divide by 2 factorial, x minus 1 squared. I have the third derivative, which is 2 over 3 factorial, x minus 1 cubed, and so on. So this is a 4th degree polynomial approximation for the function natural log of x around the point a equals 1. And you can clean it up, and it'll go into this form. We've sort of done a lot of algebra, but it's really good to understand the geometric interpretation. If you just take the first degree Taylor polynomial, which I'll call T1 of x, it's the tangent line to the graph of f of x at the point A. T2 of x will be the tangent parabola at the point A, and so on. And you might do some exercises later on the computer to help you see that. A really important question is how good of an approximation is the nth degree Taylor polynomial? And the answer is it depends on a lot of things. It depends what the function is, it depends how big n is, it depends how close to x equals a you're looking. So in general, Taylor approximation tends to be good around the point x equals a, and the further you get from that point where you've put all your information, the worse an approximation it is. So these are crucial questions that we're going to explore later. Another crucial question is, can you always find a Taylor approximation? And the answer is no way, because to calculate it, the function has to have derivatives at the point you're expanding around. So let me just give you some simple counterexamples. Absolute value of x at x equals 0. If we try to expand around that point, well, you can't take the derivative of absolute value. It's undefined, so you can't find a Taylor expansion. What about 1 over x at x equals 0? Well, you can't even evaluate the function at that point, so because you can't divide by 0. So you're certainly not going to be able to find a Taylor approximation. That's the introduction to this topic. Thanks for listening.